Again, thank you to Tom Robinson, the folks here for thinking about this and providing an opportunity to share a little bit of how the Department of Energy is thinking about artificial intelligence broadly, what we mean by it. It is a strong vision of our secretary right now, Rick Perry, to institutionalize our thinking and think broadly about our missions. I wanted to say, a little bit of background of us, just because it's a mixed audience. The lens in which I'm thinking about AI and what I mean by that specifically, I want to give a few definitions. First, we exist in our department because we have hard problems to solve. We're a mission agency. We are responsible for doing things from keeping the lights on to ensuring the nuclear security of the nation. It's a broad set of responsibilities that touches many tough problems that we are on the line to do, which lives in a space of rare events. We have to hedge against things happening that we hope never happen, so they're not instrumented. And so the kinds of things we have to do historically are to predict what could happen and put limited money against those things, because you can't do everything. And so we have to understand from information available what the risks are and how certain we are in making any decisions. Again, in terms of the missions in cyber, in nuclear, in emergency response and preparedness, we're an element of the intelligence community. We store, 700 million barrels of oil in strategic petroleum reserve salt domes in case of hurricanes and other kinds of crises. Rich set of complex missions that we turn to our laboratories, to partnerships with academia and industry to try and solve. But ultimately, we exist to solve these problems. And typically, they're problems no one else can do. If other people could do it, we would simply push the money to them and say, please do this, and it would be easy. But we end up finding that the kinds of things we have to do typically don't exist. The technologies don't exist. The research hasn't been done. The problems are just too hard. And we live in a space of extremely hard problems. And so we have turned over the years to supercomputing. We have a 70-year legacy in computing because that traditionally has been the tool in which we approach some of these hard problems. But that's changing. We have an interesting edge as we think about what AI means broadly, more in the context right now of machine learning. We have an interesting moment in time where we can do a lot of things that many others cannot. And I have to confess, it's not because of deep forethought on our part. When I was working with the labs in trying to deliver our first, heterogeneous architecture, the Roadrunner system in early to mid-2000s, which was the first petaflop system, we used the cell processors there as the graphics accelerator, the chip from the PlayStation 3. But I have to say, at the time, we were talking about interesting slow and fast modes in complex simulations. And even though machine learning and a lot of deep learning methods existed, wasn't on our radar. Largely because we didn't have the kinds of data you needed to apply these methods. And the timing wasn't right, but we actually had the tools. Since then, we've built out a number of systems. They have a remarkable set of graphics processors, Titan, Sierra, Summit, and more to come. They work, we can do remarkable kinds of graph problems there, but I wouldn't say they're optimized to that. It's just a tool it's available for us to do. But it's, again, a moment in time where we have to think seriously about these tools and the kinds of problems and how it can impact the things we want to do. But, the main point is the hardware path for AI broadly is not the same as high-performance computing. And and trying to understand something that you certainly appreciate here from the topic of this meeting is that, how do we think about the architectures and the designs and the classes of problems that we have and what that intersection is going to be. Things are moving well. Today, when we look across the globe at this remarkable technology innovation going on in learning methods being applied to every sector, it's not happening because there's been a great theoretical development that has enabled this. It's because finally the decades-old methods that people have been struggling with are readily doable by just about anyone. We have remarkable computing available on our laptops, in our offices, on the cloud, at AWS, wherever. It's everywhere now. There's a ubiquity of very powerful systems that are affordable. And today, storing petabytes of data is not an unimaginable thing. A lot of people can do that. And so when we think about petabytes, it isn't, as scary as it was 5 years ago or 10 years ago when how do you think about all this and what do you do with it? Today we think about exabytes. And so the volumes of data available, the scale of computing allow us finally to exercise methods that have existed for a long time. And it opens the door to doing things. And we've seen this boom of innovation across the private sector, again, in all economic areas that is growing. And it's an interesting time to be. It's a moment in time where there's remarkable opportunity because markets are being created, technologies are being developed, and applications are being defined. It's a place to think about the outcomes because a lot of this space is in the outcome space. People are trying to do something specific with certain types of data. It's not an abstraction anymore. Excuse me. When I think about AI, as we talk about it in the department, it's very broad. It's enabling. It's doing more than what people can do. It's dealing with the remarkable amounts of data. But ultimately, for us, it's making decisions. How do you do anything with certainty with all the data that you can get or should get, and what is the data you should have? And how is that going to change as we think about 5G coming on, in the near future and the amount of smart devices and mobility changing dramatically? What is that AI world going to be? What are the technologies we need to live in that space? And it will be different than where we are today. And so as we think about all of this and the department's role in the grid, in cyber, in all the different kinds of places, there are very important intersections with these. Now, AI, for me, is not synonymous with machine learning. We think about sensors and detectors. What is the smart way to ingest information? And we build sensors, from deploying them in satellites to deploying them in the field to measure things in all kinds of modalities. It's important to all of our missions, from national security missions to sitting on the internet nodes or monitoring the grid. Once we have data, what do you do with it? So we apply learning methods. Often, if you get it down to learning, it's the easy part, the last 5% of the problem. Data side is really non-trivial. If you've learned something, how do you decide anything? The problem with data is there is no theory of data. If this were quantum mechanics, you'd have a completeness theorem, and you'd know about the space that you live in and to what extent you're covering it. With data, you have no idea what's missing, what's there, whether the things you're trying to learn exist in the data, whether you can answer anything. But the learning methods will tell you something. And then the question is, well, how do you decide anything from that? What is the confidence? If we're making decisions that impact people's lives, which we do, is what you learn from the data truly actionable, and how do you define that confidence? And I don't mean explainable AI. I can explain how you get from A to B, but that doesn't tell you whether B is correct. That's the problem. Explainable AI is not useful for the kinds of decisions. We have to understand it in the context of uncertainty quantification, and that's a field that really doesn't exist. We care about autonomy, autonomous systems. We have everything from four different national security airspaces that we have to monitor across the DOE complex. We have tens of thousands of miles of high tension wires in distributed networks of powering the country. We own about 10% of the grid. Autonomy is an important part in emergency response and nuclear incidents. The human interface, the robotics, all of this, there are many different places where the full breadth of AI is what's on our radar as we think about how this enables success in all of our missions. AI for us lives in these data-rich environments. Often you have to do it at the source of data. The model is not the HPC model where we bring all the data to a central system and then learn. It's not going to scale that way. And we have to think about smarter ways to do it at all the different ingest points we have for the missions we do. So we care about portability, we care about power efficiency. Certainly Neuromorphic is on the radar for that purpose, and certainly the topic of this meeting is very interesting for that reason. We're very interested in exploring what the next generation of technologies, what does the post-GPU world look like? We care about that quite a bit. We know we have many different modalities of data that we're learning from. Some are long time series, some are complex information at a given point in time. We have everything from, we have medical data, we have genomic data, and years of patient histories, and blood pressure measurements, and biomarkers, for example, and EEG traces. And as you try and blend all these modalities together, what do you learn from that? How do you learn from that? There are a lot of interesting problems there. Oops. Button. And there isn't going to be a single technology solution to all of this. And whether you rely on the no free lunch theorem or whatever you want to think about, there isn't going to be, the master AI technology that is optimized to all of the problems we have, the modalities of data, the kinds of questions we want, the ways we want to do uncertainty quantification. And I think at this moment in time, with the remarkable number of startups, with the remarkable number of novel designs, this is the time to try and benchmark different technologies against the real data that we have to understand what will work in what type of context, how fast, how robust. And this is really the time to branch out and explore the technology path that is out there before these technologies harden and decisions are made. Secretary's goal is for DOE to be, become a federal lead in AI. I think because the missions we have are going to demand it, and we're working to see how to make that happen. When we think about it, it's not just about doing great science, it's in support of all of the things we do, our missions, our business, our operational functions. How do we think about all the information that is coming in through all of these? We store a lot of our cyber data. We have 10 years of cyber data stored right now at the switch in Las Vegas, sitting there. All the signals that have come across our unclassified networks. The question is, well, what can you learn from that? What do you put there? It's an interesting data set. We have all kinds of things like this. As you look through the department and you understand the problems we have, we are rich in data, and there are places to learn so we can eventually figure out how to embed these. And so when we're talking about AI, we're talking about where the rubber hits the road, where we are touching data that is impactful to things where we want to deploy the technologies. It's not about doing it as an abstraction. It is touching the real data in partnership with other parts of the department, other partners across government, with the private sector, with whomever, but trying to institute things that we will deploy. And I think partnerships are going to be a key part of this. We're supported very broadly in the administration right now, again, as a moment in time, not only in terms of technology innovation, support from the president, support from Congress. A lot of people are supporting AI, and it is the place to try and shape the policy right now that gives the top cover to do things that make a difference. Funding, direction, strategies. You know, the executive order from February of 2019 has very good broad words that I think most of you could find a way to fit something in there. Executive orders do not direct you to do anything, but they are enablers. It means that you have a justification when you try and do something new, that you're not entirely shot down because you can refer to some of the guidance from the top. And so again, we have different kinds of direction coming in, support from our top leadership, that this is the moment that we need to move ahead aggressively and lean into AI. Again, it's different than quantum, it's different than HPC, it's different than a lot of the different areas that we have traditionally worked in, because the innovation here is global. You know, it's everything from smart toothbrushes to, anything you touch today has often very narrow kinds of data that people are applying innovative methods to and defining technologies that are of interest to us. You know, the phase space of innovation is certainly not localized anywhere, and we're going to have to think very broadly and differently on the kinds of partnerships and who to engage to draw in the best ideas to shape the kinds of problems and progress that we need to make. To give you a little sense, forget about the acronyms. We could list more. Different parts of our department all have different abbreviations. But, we have emergency response functions. So we have for cyber emergencies, for grid and energy sector, we own the responsibility nationally for all energy, even though we don't own necessarily all of those infrastructures, but we still have the responsibility to make sure it stays up, or if it goes out, it comes back. And as we start layering information for CSER, the cyber security, energy security and emergency response, it's an all-hazard problem. Natural and man-made events, hurricanes coming, cyber events, disturbances from the sun, flares, all of this stuff is part of how we think about it. And as you layer information together, the question is, how do you pre-position things? How do you prepare? How do you respond? How do you advise, transportation? Where should people go to get gas? Where do you travel? The whole thing of emergency response is an increasingly complex, increasingly instrumented space where we are making decisions. In our IG, our Inspector General, in looking at internally how we manage things, so our IG has problems in looking at the records we have and trying to understand what we do. Parts of the grid that we have, the power marketing administrations, the largest one, WAPA, is the size of continental Europe. It's the size of Paris to Moscow, Athens to Oslo. It's geographically huge. It's one of the 4 power marketing administrations across the U.S. They get 96% of the revenues from pushing energy to utilities. And consequently, if they want to do research, they have to apply for a rate hike. And how many people, support when your local utility says, we want to raise your rates? Most of you don't like that. And so it's not an effective mechanism for doing research. Nevertheless, we own the infrastructure, and so what do these guys do? They have operation centers. They have a few of them across this geographical area where people work 24-hour shifts in dark rooms. We have 320 energy substations unmanned. 250 have instrumentation, so they have video feeds. Video feeds come into the room and people stare at screens. We look at change detection for preventive maintenance on the high power lines that cross the country by flying a helicopter over the lines and taking high resolution video, downloading the MPEGs to a computer where someone will look at it and compare it to last year's video. Because of the cost, it's done every 4 months at any given point in space. But it's a very kind of antiquated method where you could think of autonomous systems trained on existing data with change detection built into smart sensors that you could do things more smartly even today. They have pricing problems. You know, you'll have across this area, you have local pricing of markets that force distribution in different ways that people simply manage by looking at the market prices. So we'll have moments in time where we have to pay the state of California money to dump megawatts there. But we make money in Nevada. And so how do you adjust the loads when you have costs involved in distribution because of negative pricing and positive pricing just across a state boundary? When temperature variations, when it's very hot in the Central Plains, high tension wires sag, it's colder in the mountains, in the Rockies, you can lose up to 20% power efficiency by sagging wires, and people look at maps of temperatures and try and redistribute. But you could imagine with more smartly instrumented systems, information coming in, how you would adjust loads more effectively. And so as you try and fuse all this data together and you start thinking about this, and they have many different other modalities of data, we own that part of the grid. You know, that's a DOE asset. You know, should we be looking there? They can't do it by themselves. They have no research arm. You know, what's our position in this? What is the AI intersection of how we could draw more efficiency out of the grid, more resilience, robustness? And as you look across the department in the different things from intelligence functions to anything else, you know, you see that there are people buried in data, accepting risk because they have to make decisions based on what they can humanly ingest. And that is only going to get worse. So how do we think about this? And what should we be doing? And those are the kinds of questions we're starting to look at. And how do we draw upon the kinds of technologies that we've been looking at and that we should be looking at to do this? What exists today? What is going to be done by industry? And what are things that we think won't be done by industry and have to be done by us, are part of the menu of things we're doing? You know, there was a phase change in the use of AI in looking at what DOE does in the last year and a half as we started to move this forward. When we looked at our previous budget documents and so on in making the case, AI didn't appear anywhere in DOE documents. Today it's everywhere. You know, almost in every paragraph, everyone is now doing AI. And I would say that nothing has really changed in terms of what we do, but the labels have. And so, you know, there is a body of work out there right now, which is everyone that has data is applying the same optimization. It used to be called statistics, now called AI and Bayesian methods and whatever. You know, there is a place where we're doing a lot of application of learning methods today. So it's kind of narrow in that sense. It uses GPUs typically, neuromorphic. It is kind of a churn of things where if you say AI, there is always the anticipation it leads to more funding. Okay, so we got that. You know, and that's good. You know, it's nice that people are thinking about this and it's getting, you know, a community of people thinking more broadly about this. But it's also a distraction from the hard problems that are out there. we think about what we should be doing. This issue of uncertainty quantification, of how you make decisions, I think is non-trivial. In how we've learned to do it, probably, I would argue, best of class anywhere in the computational world is in the nuclear weapons program. And we make decisions there all the time, decisions for big facilities, decisions for refitting weapons, decisions for moving them. Things that, when you have 18 to 20-year-olds taking weapons out of bunkers and moving them around routinely, or the fact that we drive them across the country, coast to coast, north to south, east to west, in trucks you might have passed on the highway without knowing it, you care about what happens with these. If you can drive 2 miles an hour faster, we actually study that problem. If things are aging and we, things are cracked inside, if things over the decades, because these weapons are old, are problematic, we have to make decisions. Can you move them? Can you touch them? Can you take them apart? Should we fix them? And we have people that touch these all the time, every day. And so these are questions that we answer, and then we move ahead and do these things. And so when we make a statement that something is safe, there are people that immediately are impacted with that because they trust that the job they're doing is in fact safe. And we have developed means to make these kinds of very complex predictions, which is an aggregation of uncertainties in complex ways that is not simply mathematical. If we could simply aggregate all the error in quadrature, life would be easy. If you could do that after the fact, it would be easy, but it's not like that. There are many ways that uncertainties come into our problems that are not really quantifiable, but nevertheless have to be dealt with. And as we put all of this together, it has a lot of people in the loop. It is very complex, but we've developed this and we use it every day at some of our national laboratories, I would say in ways that no one else does. And I think we have a fair expertise there. But I think what I've learned from being in that process is that the extension to AI is also going to be non-trivial. The extension to learning and how you quantify uncertainty is not going to be a simple task. It isn't something that should be done as an afterthought. I believe that there will be things that we're going to want in hardware, that it'll have to be the way we think about it. The problem we've had in high-performance computing is we built uncertainty quantification around the model for simulation of a system from t equals 0 to t final. And then we dress it up with Latin hypercube or Monte Carlo methods or whatever. And we try and figure out how you build around the code the things that could capture uncertainties. And that doesn't really work well. Especially it doesn't work when you're creating petabytes of numerical data today and when you have easily petabytes of experimental data today. How do you compare these? They don't coexist in any way. And the way we do it is we reduce experiments to the simplest pieces we can use and simulation as well, and we'll put together a curve with error bars, or we'll have a spreadsheet with experiment and prediction, and we'll lose all the complex dynamical information that existed. There is no way to intersect all the experiment with all the theory. And so when I think about UQ, when I think about this intersection with HPC, a hard problem that we should be working on is how do you embed all the experimental data in the simulation and run the simulation in the data. And a couple of years ago, I was trying to get the True North embedded into our nodes from the Sierra system when it was in early delivery back in 2015 without success. We had all these PCIe slots and great node coherence, but I couldn't get IBM to put a PCI interface there and ask if we had a neuromorphic processor in there. The first thing we were looking at is mesh tangling. As you create your mesh and you do complex dynamics, things tangle, get squished, become singular, fail. Can you learn in real time by learning from the mesh and finding better ways to control the simulation. Okay, and then if you extend that, well, can you learn from the data? Could you embed all the experimental data in there and learn from the data in the same way? Could you create a simulation that lives within the data, and you, in one simulation, you figure out through the cloud of information you have how good you are? Could you rethink simulation using all the data instead of throwing most of it out? That's a direction, that's a hard problem that we should be doing. I know I'm probably out of time. I'll touch a couple of these. Adversarial AI, one of the reasons that we have to be doing this is the ways you can fool it are important. If we're going to be embedding these into our systems, we have to understand failure modes. Theory of data, of course, complex sets of architectures and technologies. We have to be exploring all of these. I'll only say a couple of things here. You know, it's a funny emerging field here, but at least it tells you why you can't be a customer in this space. Everything we're going to be doing in critical systems, in grid and cyber and national security is going to be smarter. And there are interesting ways you can fool, your adversary's latent space. You can probably find ways to make their detectors insensitive to things that you want to do. There are all kinds of things you can think about today, and they're going to be more in the future. And so AI today is fragile, but it is an interesting place, and we can't just simply buy technologies and assume that they're going to be foolproof, failure-proof, attack-proof. As we've learned the hard way in cyber, we have to be invested in this from the start. We have to be invested in understanding this side of it. And it's another reason why we have to understand these technologies inside and out to make best use. I'll only say here, Secretary Perry's priorities in AI include some passions in helping veterans in traumatic brain injury. We've amassed a remarkable amount of medical information. Relevant for this community also might be, the images we have, the MRIs, the DTIs on traumatic brain injury. Can we learn something? Are there technologies here in the neuromorphic space that we could embed in that data to learn more from the rich image sets that we have from thousands of medical images? Are there places? That's something we could try and do if there were things that were ready, and surfacing those would be nice. But we have, anyway, a rich set of problems here, all kinds of data in mission and through partnership with others, where tools and methods need to be developed, and we're ready to try and implement new ideas. So let me just try and bring this to some kind of conclusion here. It is perhaps the most exciting time in technology that we've had in decades, and maybe it's reminiscent to the early and mid-90s when we were going from vector machines to massively parallel, and there was the churn of intellectual churn, the startup companies that came and went, many different computing paradigms that people were thinking about. And then eventually in the late 90s, this settled out, and we've been living on that for the last, almost 20 years. But we're now in this space again. There are these fabulous companies building out novel chips at TSMC or Samsung or pick your fab. There are big companies and small invested in next generation ideas, dozens and dozens of these. And we talk to a lot of these. These won't be here probably in 5 years' time. We don't know what all these technologies do. Most of them are looking to find market, maybe in the cloud. Hopefully, AWS or Facebook or someone will buy their accelerators and they'll find some mission. I would argue we have some fairly unique missions and data needs that won't be met if the selection process is done through those methods. And partnering now to find out the best technologies to use is a unique moment in time. And it'll freeze out when a lot of these companies go away or are bought out. And so this is the time really to explore. I don't know what the metrics are for performance against the kinds of data we have. I don't think there'll be a single measure that will do well. I don't want to redo a LINPACK measure for these kinds of technologies because we've been wrapped around the axle on things that codes that don't work well on our systems, even though the LINPACK is remarkably high. And so thinking a little more thoughtfully about the technologies that we need, the measures against the classes of data will be important. I think if we solve some of these problems, they're going to be important. And I think we have a responsibility to do that. And so I would certainly encourage you to think about places we could do stuff. For us, it's going to be about touching real data and making things happen, developing tools that we will deploy into the field that lead somewhere. Not prototypes, but actually things that we will test, use, and move ahead on some kind of technology path. The more we can surface today, the more ideas we can develop, the better. It's an interesting intersection of technology, of frontier science, and of real mission need. And it's a great moment to be thinking about this today, and it probably won't be here in 5 or 10 years. So this is really the time to churn through this and define a future which makes a lot of sense. Any help you have is certainly welcome. So thank you.
Thank you very much, Dimitri. Wonderful talk. We have time for probably one, maybe two questions.
Total clarity.
I have one. Could you expound on the data theory idea a little bit?
So, this is a hard problem. First, we don't have a real data policy in the department. We don't know exactly what to measure. Understanding what you need with a sense of the future is important. I've seen remarkably curated data sets that other agencies have gathered over the years, which were in the mode of use of an analyst will look at this and learn something, and for that purpose, it's wonderful. The modality of use is that. For learning, useless, because the information isn't tagged in the right way without someone actually going through and doing everything. So the mode of use of the data was not thought out with enough clarity to make this useful for today's technologies. Today we think about deep learning, we think about these methods, and we're certainly positioning data to be useful for that, but deep learning is not new. It goes back years and years, and the question is, what's coming next? What is the data we need? Now getting back to your question, Tom, the challenge we have is we care about rare events. The things we worry about are typically catastrophic things. That's why we exist. That's why we have national laboratories. That's why we tackle hard and unusual, often esoteric problems. And so necessarily, the kinds of things that we want to understand are not in the data, and we know that. Nevertheless, we're going to be measuring all kinds of things, and so the question is, how do you learn about where the cliffs are if you're only measuring the plateau? How do you extrapolate? How do you understand decisions in that way? What does decision mean? And the problem is, in your data, you don't know exactly what's there. The data is incomplete in many ways. And we don't have a sense of what completeness means. What is missing from any data set? I don't think, it might not be a well-posed question. Question is, what are you looking for? What are the kinds of questions you're asking of the data? And so it is probably a question that is similar to what's the zone of validation of your code. Well, it depends on the kinds of questions you're asking of it. And so there are probably questions that are answerable within your data, and there are probably some that are not. And the question, how do we understand that? If we're going to be making decisions, and if you had explainable AI, it wouldn't answer that question for you. And so how do we understand the theory of data? What does it take to do that? Is that a reasonable thing to try and do? We certainly should try and understand whether we can understand it, as an entry point into this. It'd be nice to have more clarity on what the right data is. We can't measure everything. We can't store everything. But we have remarkable sensors and measurement capabilities and storage capabilities today. We can measure a lot more than we currently do. What should we measure? Measuring everything blindly doesn't make any sense. How do we smartly measure things, and how do we make sure the data we measure is positioned for the tools that'll be here in 10 years so that we're not in the same place of, well, you made that for deep learning, it's no good for this. How do we add the flexibility in the thinking of the data with more foresight than we have done historically? The same thing with the medical data we have. Medical data is made for bookkeeping, for issuing, for costs, for billing purposes. It's not made for research. We try and use it for that, but the billing codes are different than the kinds of things you'd want to do medically in terms of understanding issues and concerns. So again, it's the data we have, but it's not great data in that capacity. How do we have more foresight into the data world rather than taking for granted that data exists and we're going to do something? And so we have to think about this whole enterprise holistically. Kinds of data, its modalities, how you do anything with it, and how you make any decisions from it that you believe are actionable. If lives depend on it, if huge budgets depend on it, how certain are you, and what is the guarantee you could provide? These are places that we have to be working, and these are places we're going to go, and help in thinking that through will be important.
Well, thank you very much.